Okay, here we go. Part two. We're back. Okay, guys. So lone pairs take up more space. So if there's a lone pair, the angle is not the same as the base angle. Okay. Tetrahedral. The angles are 109.5 degrees. That is assuming that all of the atoms are the same, and they are all atoms that are bonded. Right. So in the tetrahedral shape, all of these are going to be. We're going to call them 109.5. But when there's a lone pair on top, like there is here, the shape is no longer tetrahedral. This is what we call trigonal pyramid, because it's a pyramid with the base of a triangle. The angle is going to be slightly constricted. So on the bottom, instead of 109.5, it's generally around 107. Whereas the angle above is something greater than 109. Call it like, 111 or something like that. Something bigger. If there's 4 domains, but 2 are bonded, 2 are not, then we have the shape that is bent. And if it is bent with the 2 lone pairs, then the angle gets constricted further. So this angle here is going to be around 104.5. Now, you're not going to be asked to recite what the specific bond angle is. You have to understand the concept. Lone pairs take more space, therefore they constrict the bonded atoms, and the bond angles get decreased. Okay? If you understand that concept, you're fine. That's what you need to explain, but you're not going to have to tell me the literal number. Okay. Oh, wait, look. This is what I just talked about. Non-bonding pairs are larger than bonding pairs. Now, additionally, look at this guy. The difference here is that this domain is a double bond, and because you have 2 pairs of electrons in a double bond, they are also wider and will take more space. And they will also constrict the bonding angle a little bit to some degree. In this case, it goes from 120 to 111.4. So that's actually a little bit more constriction than we saw in the other examples. Again, don't need to know the exact numbers, right? Just understand the concept. Okay, what shape is this guy right here? Molecular shape. 3 domains, all bonded. Trigonal planar. Yep, trigonal planar. Okay, then this is what we just talked about. Okay, so here's the thing. When you guys were sophomores, we stopped after 4 domains, because 4 domains are the naturally occurring domains found in molecules. Under artificial conditions, we can see domains larger than that. They're called expanded domains. So if you have 5 domains, you end up with a shape that it looks like a combination of trigonal planar and a linear. Like the linear goes up and down. This geometry has 2 axes. The vertical axis right here in purple, this is what's called the axial plane. And the triangle around the midsection is called the equatorial plane. So the equatorial plane is, if you look at it, that's where your trigonal planar is. The axial plane is where your linear is. You guys see that? You combine them together, you get a trigonal bipyramid. So the base name for 5 domains is trigonal bipyramid, because it's a pyramid above and below. Bipyramid, 2 pyramids, triangle base. If you have a lone pair, so 5 groups total, 4 bonds, 1 lone pair, the lone pair will be on the equatorial plane. Okay, so lone pairs on the equator. That is where they must be. And the reason why they must be there is because there's more room around the waistband here. There's more room here than there is here. This angle here is 90, but around the waist it's 120. Because lone pairs take more space, they have to exist where there's more space for them to exist. So that's why the lone pairs will always be on the equator. Now the name of this shape is seesaw, because if you put it on its side, it literally like rocks back and forth like a seesaw. And I'll show you with the physical models here in just a second. Let's just get through the chart. All right, 5 domains, 3 bonds, 2 lone pairs. Remember, lone pairs have to be on the equator, so both lone pairs will be on the equator. And this is what we call T-shape, because if you turn your head sideways, it looks like a T. If you have 5 pairs, 2 bonds with 3 lone pairs, the 3 lone pairs, all 3 of them will be the equator. Okay? And your bonds are just in the linear shape. So the name of this shape becomes linear again. So the 5 pair family is the one that requires the most thought to process when you're looking at it and you're trying to determine the shape. The last family is when you have 6 domains. When there's 6 domains and they're all bonded, we call this octahedral. Octa, 8, hedron, sides, so 8-sided. Okay, so if we were to draw one, it's kind of like an Egyptian pyramid. That's a terrible pyramid, but can you guys see what that is supposed to look like? Here, maybe I'll draw in here. Here, 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 here. Right? That's a pyramid on top. There's 4 sides on that pyramid, and then the bottom half is 4 sides. That's why it's 8-sided. Octahedron. If there are lone pairs in an octahedron, then determining where they go doesn't matter, because here they're all the same. Every angle here is 90 degrees. Right? So 90 degrees. So the lone pair, just pick a side. Put the lone pair there. If there are 2 lone pairs, then the lone pairs will be placed oppositely of each other, because that is the most symmetrical arrangement. That is how the lone pairs can be placed the farthest apart. And that's what we call square planar, because it's flat and it's a square. Whereas this one was square pyramid.
Why would the square pyramid not be bent at all?
Say again?
Why would the square pyramid not be bent at all? Like with the one pair on the bottom, like when the ones on the side?
Okay, yeah, so I see what you're saying. So why wouldn't it be like the bonds get pushed up a little bit?
Yes.
Is that what you mean? So they might be, but the 4 bonds there, the fact that there's 4 bonds there, and you have a lone pair that's repelling against 4 bonds, the effect on one lone pair pushing against 4 bonds is not, it's kind of negligible. So it probably does happen, right? But it's not happening to the point where we're going to mention that it changes the angle. Okay. All right. So let's back out for a second and look at these. What you need to be able to do right now is you need to be able to draw a Lewis diagram. You need to be able to assess the geometry. So which shape is this? And the easiest way to do that is to first put it into a category. Is this a 2 pair, 3 pair, 4 pair, 5 pair, 6 pair category? And once you're in that category, then assigning the shapes becomes a little easier. Now, whenever there's a lone pair, the lone pair throws the electrons, the electron density, it throws it off balance. And if the electron density within a molecule is off balance, that's going to result in a polar molecule, because you got electrons not equally distributed in all of the directions. Okay, so let's go through these here. So the linear, the left side and the right side, do you see how it's perfectly balanced? This would be a nonpolar molecule, okay? Could this be one be polar? It could be if this left atom and the right atom are not the same, then that would be polar. But if it's the same atom on both sides, it would be nonpolar. Trigonal planar. If these three atoms on the outside are all the same, this is a nonpolar molecule. Everything's balanced. But if one of these is different, see, like if I gave you a molecule like this guy, like this. Okay, that's formaldehyde. This is trigonal planar, but the oxygen is not, the electronegativity of the oxygen is not the same as the hydrogens. So electrons would be pulled more to this side. So this would be polar, whereas this is nonpolar. Does that make sense? Okay. Lone pair here clearly throws off the balance, definitely polar. Tetrahedral. Is this polar or nonpolar? It's nonpolar provided that all the atoms are the same. If one of them is different, it becomes polar. Here, there's no way for this to be nonpolar. This is definitely imbalanced. Bent, definitely imbalanced. Let's go to the new families. 5 pairs. If all 5 are the same, this is nonpolar. If you have a lone pair, there's now an imbalance. This is polar. If you have 2 lone pairs, this is polar. If you have 3 lone pairs, do those lone pairs act equally and in opposite directions? Yes, they do. So the effect of the lone pairs cancels itself out. So this one would be nonpolar, right? Nonpolar, assuming the top and bottom atom are the same. Octahedral. Same atoms in all 6 positions, nonpolar. Square pyramid, definitely polar. Square planar, nonpolar. So if it has a lone pair, it doesn't automatically mean it's polar. You have to kind of assess, because we saw 2 instances where there are lone pairs, but this guy and this guy are nonpolar. Yeah, you're looking for symmetry, but be careful. Also pay attention to if all the atoms are the same. Yeah. Mattia. If they have the same electronegativity, then we would consider that a nonpolar. Yeah. All right. That's enough.